Our next problem, number 5. A buffer solution contains 0.12 moles of propionic acid and 0.1 mole of sodium propionate, which is its conjugate base, and that's been dissolved into 1.5 liters of solution. We're being asked to calculate the pH of our solution. Again, a Henderson-Hasselbalch, pH is equal to pKa plus the log of the ratio of the base over acid. We have to do a little molarity work. Moles per liter will contain our molarity. So let's just solve for moles of acid first. And if we look at the acid containing 0.12 moles over the 1.5 liters, I'll hit that 0.12 divided by 1.5, and I'm finding 0.08 molar for the acid, HA for acid. And its conjugate base is the propionate anion, C3H5O2 negative. Its number of moles, 0.10 mole over the 1.5 liter, pulls out molarity. 0.1 divided by 1.5, and this has a value of 0.067 molar units for the conjugate base. To calculate pH, we need pKa. Let me use my Appendix D to find propionic acid, listed in the P's. 1.3 times 10 to the negative fifth, plus the log of the ratio of base over acid. The base is coming from the conjugate base here, sodium propionate, 0.067 molar units, divided by the concentration of our acid, 0.08 molar units, base over acid. Hitting for pH, we come up with negative log of 1.3 E negative 5 plus the log of the ratio of 0.067 divided by 0.08. This pH of this buffered solution is 4.81 pH units. Letter B. What is the pH of the buffer after adding 0.01 moles of NaOH? So, if we're adding a strong base, a base reacts with the acid. Let's consider the chemistry first. If OH negative reacts with lactic acid, I'll just simply write as HA, it is going to neutralize the acid to form water, giving me more of the conjugate base, A negative. Remember, HA is standing for the lactic acid, and A negative is standing for the conjugate, the lactate ion, or propionic acid and propionate ion. Okay, so here's what we know. Before the reaction occurs, we know we have 0.01 moles of base, and we know that we have 0.12 moles of acid. Notice I'm using moles. Coefficients stand for moles, not molarity. And on the opposite side, the conjugate base coming from sodium propionate gave us 0.1 moles before the reaction occurred. The limiting reagent is hydroxide. So during the course of the reaction, it gets used to have no value left. It will also use 0.01 moles of the acid along the way. 0.12 minus 0.01 leaves me 0.11 moles of solution. And products get made to the same amount. 0.01 moles would be added, giving us 0.11 moles of the conjugate. So after the strong base has been added, we now see the number of moles of acid to be 0.11, and the moles of its conjugate base also to be 0.11. When we place this into the Henderson-Hasselbalch, we need the molarity units. So we'll need to remember to divide out the 1.5, although we're seeing that this will cancel out, but we'll show the work. 0.11 divided by 1.5 gives us a molarity of 0.073 for both the acid and the base. So pH is found using Henderson-Hasselbalch as negative log of the concentration of Ka. 1.3 times 10 to the negative fifth is the propionic Ka, plus the log of the ratio of base over acid, which we said both came out to be the same number, so we can see this portion just dropping out. So when they are indeed the same, pH does equal pKa. So we'll hit negative log of 1.3 E negative 5, and our solution now has a pH of 4.88, 4.89, rounding better. So here's what's happened. The buffered solution started at 4.81. We added a strong base, and it budged a little. It went from 4.81 up to 4.89 pH units. Letter C goes right with this same buffered system. Let's calculate the pH of the buffer after adding the strong acid, HI. So again, let's consider the chemistry. HI, again, let's just write that as hydrogen ion. The strong acid reacts with the base, A negative, and I'm using that to just represent propionate, the negative ion. And when it does so, we form more acid, HA. Adding a strong acid decreases the base and makes more of the acid in our buffered system. So here's what we know. Before the reaction, we had 0.01 moles of the acid, and the conjugate base was 0.1 mole. See how I'm pulling that from way up here? 0.1 mole of sodium propionate. And before the reaction, we had 0.12 moles of the acid, HA. Reactants get used and products get made. The hydrogen ion definitely is the limiting reagent and will be left with 0 value. It will also consume 0.01 moles of the initial 0.1 mole of the acid. 10 minus 1 is 9, so 0.09 moles of the conjugate base are left over. And products get made, so we're going to be adding 0.01 moles to give us a new value of 0.13 moles in our new solution. Remember that when we use Henderson-Hasselbalch, it has to be molarity units, so remember to divide by that original volume of 1.5 liters. Let's calculate the pH after the addition of a strong acid. pH is found by taking the negative log of the Ka value, 1.3 times 10 to the negative fifth, plus the log of the ratio of base over acid. The base, 0.09 moles per 1.5 liter, is its molarity, and the acid has 0.13 moles over the 1.5 liters. Solving for pH. Negative log of 1.3 E negative 5 plus the log of the ratio 0.09 over the 1.5 divided by 0.13 over its volume of 1.5. Now the pH is 4.73 pH units. Recall what's happened? We started with a buffered system that originally had the volume of 4.81. After the addition of a strong acid, it went down a little. Our number makes sense.